on how things go, so be prepared for that. But let's start with Vadim, who will give his talk remotely on nuclear shadowing in exclusive processes. So Vadim, you just go on, and in case there's any problem, we get back to you. But other than that, you assume that we hear you well.
Okay, very good. Yes, good morning. Thank you for accommodating my remote talk. So I will talk on nuclear shadowing in exclusive processes. You see the outline. First, I will give a brief introduction on nuclear PDFs at small x and what can be learned about them using ultraperipheral collisions. That is, collisions of ions at large impact parameters. Then, in the main part of my talk, I will discuss what information on gluon nuclear shadowing one can extract from coherent J-psi photoproduction on nuclei using heavy ion ultraperipheral collisions in the LHC kinematics. And then I will briefly discuss and mention theoretical issues in PQCD studies of this process that has been discussed in the literature recently, and in the end, I will conclude with mentioning that obviously studies of exclusive J-psi, exclusive charmonium photoproduction on nuclei contains information on the impact parameter of the gluon distributions in nuclei. That is, one can learn about imaging of nuclear gluons at small x in nuclei. If you heard my recent talks on this subject, you will see that actually I will repeat many things. I've given this talk a number of times recently, and every time I was hoping to go beyond the approximations that we were using for last 3-4 years. It's still work in progress. Now I'm in Uvascular for a year trying to make some progress, but still it's work in progress. So I will have to repeat many of the results and many of the statements that you have already probably seen before. So let me start with my brief introduction on nuclear PDFs and nuclear at small x and nuclear shadowing. This is my slide 2. So nuclear shadowing, just a small repetition, nuclear shadowing is a suppression of nuclear PDFs compared to the sum of the nucleon PDFs at small values of Bjorken x of the light cone momentum fraction x smaller than, say, 5 times 10 to the minus 2. Obviously, this quantity, collinear nuclear PDF, is an important ingredient of QCD phenomenology of hard processes in nuclei because it quantifies so-called nuclear matter effects. It's important for the quantitative estimates of gluon saturation, and in general, it's an important quantity for phenomenology at all the available and future colliders. At the moment, these nuclear PDFs are non-perturbative quantities, which at the moment are determined using the so-called global QCD fits. That is, one assumes an initial shape of nuclear PDFs, performs the D-Glab evolution equation, compares to the data at the given resolution scale, goes back, corrects the shape, and this way determines the shape of nuclear PDFs. So one uses the fixed target data on deep inelastic scattering on nuclear targets, data on certain hard processes, in particular pion production in deuterium gold scattering at RIC, and recently certain hard processes such as dijet and the gauge boson production in proton lead scattering. And using this wealth of data and performing global QCD fits, one extracts nuclear PDFs, that is distribution of quarks and gluons in heavy nuclei. Examples of such an analysis are presented in the 2 panels below. And the left one, I show the ratio of the gluon distribution in the heavy nucleus of lead to that in the gluon distribution in the proton. at the fixed resolution scale q squared equals 10 GeV squared as a function of the light cone momentum fraction x. You see different curves with the associated error bands. These are results of 3 different groups. And you see that fitting essentially the same data, different groups obtain quite different results with shadowing, without shadowing, with anti-shadowing, this bump here, without it. And so that shows, and then the plot on the right shows an even more recent analysis of the EPPS 16 group when one indeed adds the PA at the LHC data, and one sees that it doesn't help much. So one still sees very significant uncertainty bands on the predictions for this gluon, let's call it gluon shadowing ratio. So we've been working with, that is we, Frankfurt, Guzey, Strickland, we've been working on the alternative model-dependent approach, which allows one to predict nuclei PDFs at small x. So, and we advertise our approach as an alternative to the uncontrolled extrapolation of the global QCD fits to small x. This is the leading twist nuclear shadowing model, which I will not discuss, but which I will show that agrees quite well with the data on exclusive J-psi photoproduction that I'm going to discuss later on in my talk. Let me go on the next slide. Of course, the situation will be dramatically improved in the future when the data at EIC or LHEC will be taking, mostly because of the wide q squared x kinematic span. This is shown on the panel below. This is a well-known graph from the EIC white paper, and also due to the measurement of the nuclear longitudinal structure function FL, and also to the measurement of the charm component of the structure function. The diagram for the charm component of the inclusive measurement is shown in the plot here, and the panel on the right shows what will happen, shows the simulated results of what will happen when on top of the existing, that is gray error band prediction for the gluon shadowing ratio, one adds pseudo data, EIC pseudo data, does again the global QCD fits. See that, of course, with the newer data in the wider kinematic range, one will constrain the gluon distributions in nuclei much better. Before it happens, one has to resort to other means, and one of the ways that we've been advertising for last 4 years or so is a particular class of processes at the LHC, which are called ultraperipheral collisions. So ultraperipheral collisions, UPCs for short, are collisions of heavy ions when they interact at very large impact parameters, which are larger than the sum of their radii. In this case, since the transverse distance between the two nuclei is large, the strong interaction is suppressed, and they the nuclei interact via emission of quasi-real Weizsäcker-Williams photons. An example of the process that I'm going to discuss is coherent exclusive J-psi photoproduction in UPCs in ultraperipheral collisions of ions B and A. In this case, ion B emits a quasi-real photon, which interacts strongly and coherently with ion A, and produces J-psi, for instance, in the final state. In the experiment, the UPC, the signal of UPCs is very clear because it's an electromagnetic probe. UPCs correspond to an empty detector with only 2 lepton or pi tracks from the decay of the final state vector meson. So experimentally, such processes can be tagged very, very easily. Sorry, I go back. So the cross-section for coherent photoproduction of vector mesons in UPCs is given by this expression. There are 2 terms, because each of the ions A and B can serve as a source of photons and as a target. And each term, in turn, is a product of 2 factors. The photon flux emitted by, say, this ion, times the cross-section of photoproduction that we want to study, that we want to extract, that contains the interesting physical information for us. The photon flux is known from quantum electrodynamics, and it's characterized by high intensity, which scales as the nucleus charge squared, and the high photon beam energy because of we consider ultra-relativistic collisions when the photon energy is in the target's rest frame scale as the Lorentz factor of the emitting nucleus squared. And usually the cross section is expressed as a function of y. Y is the rapidity of the final state J psi. So by measuring the rapidity of J psi, this is exactly what is done in experiment. Using the simple expression, knowing the collision energy, we can reconstruct up to the ambiguity that there are two contributions. We can reconstruct the invariant photon nucleus energy. Therefore, we will know the Bjorken X of the gluon that we probe in this process. But let me come to it a bit later. So just a brief summary of what has been done so far during round 1 at the LHC and what people want to do and are doing in round 2, which goes on now at the LHC. So to probe protonic structure of nucleon and nuclear targets, one needs to select UPC processes with a hard scale. Therefore, if one considers vector mesons, one considers heavy vector mesons, that is charmonia and batamonia. And also recently, one also studied dye-jet photoproduction in ultraperipheral collisions. So during round 1, one studied J psi and psi prime photoproduction in lead-lead, proton-lead, and proton-proton ultraperipheral collisions, and also photoproduction of batamonia, radially excited states in proton-proton and proton-lead ultraperipheral collisions. And also studied soft process of photoproduction of raw mesons. I'm not going to discuss it in my talk. In round 2, on top of the processes that I already mentioned here, one also for the first time studied dye-jet photoproduction in UPCs. These are the two. This is the process. Let me just move something from my screen. These are the processes shown here. There are two contributions. Direct photon contribution when the photon enters directly into the hard scattering part. These are the leading order diagrams. And the result photon contribution when the photon contributes in the hard process via its protonic structure, quark or gluon photon PDFs. Again, this is an interesting process that at the moment I'm working on, making predictions for the rates, comparing to the Atlas results. I'm not going to talk about it. I'm going to present sort of the old stuff, exclusive J psi photoproduction, and what one can learn about nuclear gluons using this particular process. Okay, let me continue. So why J psi and why nuclear gluons? So the story starts in, for us at least, 1993, when it was shown that in the leading logarithmic approximation of PQCD and the non-relativistic approximation for the charmonium wave function, the differential cross-section of, for instance, J psi photoproduction on any target T is proportional to the gluon density of the target squared. The factor of proportionality in this approximation is derived, and it's expressed in terms of the strong coupling constant and the leptonic decay width of the J psi meson. The resolution scale of the gluons is given by in this non-relativistic approximation by the mass of the J psi, and also the momentum fraction x carried by the two gluons in this two gluon ladder is also fixed by the invariant collision energy and mass of the J psi. Of course, after that, many people used various approaches trying to improve on this simple leading order results. And here I list several quite distinct approaches. The most probably fruitful one was based on the KT factorization, where people sort of mocked up next to leading effects to this formula and built quite successful leading order and NLO PQCD phenomenology, which successfully described the measurement of this process at HERA and later at the LHCb and the LHCb on the proton. The approach which is most relevant to the scope of this of this program is the approach based on the collinear factorization and GPDs, and this is the last one mentioned at the bottom of the page. The calculation has been done, the formulas are known. When you try to apply it phenomenologically, you'll see that analog corrections are large, therefore the scale dependence is very large, and in my understanding that it's no good for phenomenology. One needs to work a bit more to make it more useful. And again, I will mention it a bit later. So using what can be called Riskin's formula, one can apply it both to the nuclear targets and to the proton targets. That's what we did in 2013. So we applied the Riskin's formula to nuclear targets, and it immediately gave us the expression for the J-psi, for the exclusive cross-section of J-psi photoproduction on a nuclear target, which we integrated over T. So as you know, previously it was differential cross-section. Now this is the T integrated cross-section. So it has several of these components. So this is the elementary. Let me omit this one. I will come back to it in a second. So the elementary cross-section, which we know from the direct measurements at HERA or LHCb, the gluon shadowing ratio squared, the nuclear form factor squared. This is because the coherent process of the T dependence is given by the of the cross section is given by the form factor of the target squared. When we integrate it over T, we simply integrate the nuclear form factor squared, and this prefactor kappa squared is a small correction at the order of 5 to 10%, which originates from different skewness of nuclear and nuclear GPDs. And again, I will later give the explicit formula, a formula for this kappa. So then we said that, okay, this is the full expression. Let's also introduce the well-defined impulse approximation. Well-defined meaning that we can define it theoretically, and this is the formula, but each of the two factors we know from experiment. So the elementary cross-section and the nuclear form factor squared. So although this is a theoretically defined quantity, we know it directly from the experiment. Then we introduce the nuclear suppression factor of S by taking the full result divided by the impulse approximation, taking the square root. When you do that, you see that the nuclear suppression of S is given by the kappa, which is close to unity, times the gluon shadowing ratio. So the advantage of this, not even a trick of this idea, is that the left-hand side, the nuclear suppression factor of S can be determined model independently, directly from the measurements of the J-psi photoproduction on the nuclear targets, on the ion of lead, and on the proton. At the same time, the right-hand side is nothing but the gluon shadowing ratio, which we can take either from global QCD, global fits of nuclei PDFs, or take from predictions of this approach of the leading twist nuclear shadowing, which I briefly mentioned. So we did that, and that's how the results look like. So the nuclear suppression factor of S is plotted as a function of X. Remember, X is the mass of the J-psi squared divided by the W squared. There are two measurements, two data points from ALICE, one more recent data point from the CMS measurement. So this is directly from the data, can be inferred from the data, and then they can be compared to the predictions for the gluon shadowing ratios in the leading twist approximation. That's our approach, and in 3 versions of nuclei PDFs. So I took 2 versions with small, with predictions of small gluon shadowing. They are obviously disfavored by the data, and the EPS09 nuclei PDFs, whose central prediction goes straight through the data points, but as I showed before, based on the existing data, EPS09 has very large uncertainty, which is given by this band. So the good agreement with the ALICE data on coherent JSI photoproduction gives modular the approach that we use direct evidence of large gluon nuclear shadowing. So at 10 to the minus 3, the ratio of the gluon distribution in the nucleus to the proton is 0.6. This is very large suppression. Color dipole models, on the other hand, generically, correspond to much smaller factor of S, somewhere here, simply because JSI, being a heavy vector mesons, favors quark anti-quark dipoles of small transverse size, and these small dipoles are shadowed or attenuated rather weak, which corresponds to the suppression factor, which is close to unity. And that was shown in, for instance, in the paper by, in the early papers on the subject, but recently when people introduced the so-called proton shape fluctuations, the agreement between the description of this process within the dipole framework and the data has become better. So, but it's still, the verdict is not out because there is large dependence on the shape of on the form of the dipole cross section, on the choice of the JSI wave function. So it's somewhat difficult to make a definite conclusion that all the versions of the dipole models are ruled out by this particular data. And then more recently, for instance, in the recent Quark Matter 2018 conference, they showed the LHCb data already at 5 TeV on the same quantity. And this is again the cross section of exclusive JSI photoproduction, the function of rapidity, experimental points sitting at rather large rapidities, which correspond to 10 to the minus 2 and higher. So these points correspond to the region of X where the effect of nuclear shadowing is not that pronounced. Therefore, it's not surprising that different predictions, different curves, which deviate at small x, they of course all converge the impulse approximation at larger x. So although this data is there, you see that it doesn't distinguish very strongly between different models apart from several models which are clearly off. I'm not going to discuss it at length. It's just for completeness that the work continues. There are new measurements for different collaborations at the LHC, and people are interested in the field and interested in these measurements and interested also in their proper theoretical interpretations. And that's what I'm going to discuss next. How can one go beyond this leading log approximation that I mentioned and put this data on the solid theoretical ground such that it can be analyzed using global QCD fits. So let me mention a few theoretical issues that I'm aware of and bring up and raise a few questions, say, and things to discuss, and mention a few things that I'm thinking about now, try to improve the framework that we used in 2014. So Riskin's formula that I showed before is derived in the leading alpha s log q squared log 1 of x approximation and the non-relativistic approximation for the charmonium wave function. Now, of course, we would go beyond this approximation. We would relax this condition and use collinear factorization for hard exclusive processes and apply it to the process that we want to study, JSI photoproduction, and we can do it at leading order and next to leading order. In this framework, the amplitude of the process is given, as we know, by convolution of generalized partial distributions of the target, gluon GPD, and core GPD at next to leading order with hard coefficient functions that can be hard coefficients which can be calculated order by order. Regarding the final state matrix element, one normally still uses the same non-relativistic treatment, and so all the information about the J-psi wave function enters through one matrix element. So here there is no difference from Riskin's approach. So this program has been done, and in the papers by Ivanov and et al. And it was shown that NLO corrections and scale dependence are large. So in the Hera kinematics, these are 200% corrections, which actually change the sign of the amplitude. Therefore, it's clear where the large effect come from. It's not clear what to do with them. One probably needs to do some kind of resumation. It's beyond the level of my expertise, so I'm actually waiting for some new results on this to appear in the literature. Because in our approach was very, very sort of simple-minded, as you could probably already glean from what I presented here. So in our approach, we took Riskin's formula at face value. The only thing that we did is that in Riskin's case, mu squared is fixed at 2.4 GV squared. We used mu squared as a free parameter and moved it a little bit up, just keeping in mind that some relativistic corrections can increase the scale of the gluons that are probed in this process, such that we describe, and so we moved it and increased it actually up to 3 GV squared, such that Riskin's formula corresponds to the W dependence, which agrees with the Hera data for J-psi photoproduction on the proton. And then we applied the Riskin's formula to the actual data. We see that while the energy dependence of the data is reproduced by construction, the magnitude is off. So we're off by a factor of 2. So this probably should be taken as a sign that the corrections that I mentioned in a few slides ago are that large. That is, the relativistic correction to the expression that we use decrease the magnitude of the formula that we use by 50%. Our approach actually is equivalent to the collinear factorization, to the proper collinear factorization at leading order, because at leading order we know that the amplitude of the process that we're considering of J-psi photoproduction is expressed in terms of the gluon GPD. At high energies, we're dominated by the imaginary part. Therefore, we enter the most skewed situation when the amplitude in terms of the GPD, when one of the gluon carries 0 light cone momentum fraction, another one carries the light cone momentum fraction of X. And then we connect these most skewed GPDs with PDFs in a model-dependent way using the so-called Shuvaev transform. This is a high-energy approximation, which assumes that the skewness comes solely from the deglap evolution of GPDs. And then in this small x or high-energy approximation, assuming that the gluon density as a function of x behaves as 1 of x to the power of lambda, the connection between GPDs and PDFs is given by the analytic formula that is shown at the bottom of slide 11. So this is this factor of R. That's essentially the approach that we use. That's the correction that we apply to the data when we describe it. Then when we took the slide 12, when we took the ratio of the nucleus to proton cross sections, when we formed our nuclear suppression factor, we found that since the energy dependence of nuclear PDFs and proton PDFs is slightly different, therefore the skewness correction factor is slightly different from nuclear GPDs and proton GPDs. This is the factor of kappa that is shown here. And although separately RA and RN are big, they are about 40%. That is, in this most skewed situation, GPDs differ from PDFs by 40%. When you take the ratio, most of it cancels, and kappa is a factor of 0.95, 0.9 at most over a wide kinematics wide kinematics of that we consider. So so when one forms this ratio S, one hopes that indeed many of the corrections that I mentioned, and they're definitely there individually for the nucleus and the proton cross-section, cancel in the ratio, and indeed the ratio of S measures directly at leading order the gluon shadowing ratio, and that should yeah, that's the hope, and that's actually a to-do list of things that one needs to check further, both at leading order, at next to leading order, and again, I mentioned this is something I'm doing now from the phenomenology point of view. It's not finished, so I'm just again listing this only the issues that needs to be checked. That is, again, I will repeat, one needs to check to what extent the connection the connection between GPDs and PDFs cancel in the ratio. That is, if S is indeed a robust quantity probing nuclear gluon shadowing. Also, one needs to check to what extent corrections beyond collinear approximation cancel when you take such a ratio. And again, a useful guide to do it is to use a different framework, to use a framework of the color dipole model, which contains subleading contributions, and again apply it to the nuclear and proton targets for this process, and see again to what extent S is given by RG. Another interesting question is to study relativistic corrections to J-side distribution amplitude. This is something that people in Uvascular, I know, were interested, and I think they're soon going to release their results. They found some interesting corrections and quite significant corrections coming from the relativistic motion of charm quarks in the final state. This is not alpha S expansion. This is expansion in the velocity of the charm quarks. These effects also affect the amplitude that I'm discussing. Okay, next slide, titled "Imaging of Nuclear Gluons." I'm approaching the end of my talk. So the formula that I used for the analysis that I presented is given here. This is the upper line, and this formula assumes that something that was say assumed in the earlier years of GPDs, when the X dependence factorizes from the T dependence. This is the sort of a factorized ansatz when the T dependence of the J side differential cross section is given by the nuclear form factor squared. This is an approximation valid in the limit of small nuclear shadowing. Now we know that the gluon shadowing is fairly large, and it actually couples to the X dependence. So the correct formula to use, at least for studies of the T dependence of this process, is given in this line, and the quantity which enters is the sort of generalized gluon density, still in the limit x1 equals x2. X1 and x2 are the light cone momentum fractions. But this is the two gluon form factor squared, essentially, this box quantity. Then when you make the Fourier transform of this quantity, GA is a function of X and T, you end up with the nuclei PDFs in the impact parameter space. And in the leading twist nuclear shadowing model, the expression for this quantity is known, and it is given by this long expression. This is just to illustrate that the approach of this leading twist nuclear shadowing predicts both X and impact parameter dependence of C quark and gluon distributions in nuclei, and the effect is quite sizable because nuclear shadowing is stronger at the center of the nucleus. Therefore, there should be correlation between the impact parameter, again, the impact parameter dependence of nuclear PDFs, and the light cone momentum fraction dependence of nuclear PDFs. And the effect is shown here. So the use of the full formula of this one for the differential cross-section is given by the red curve, and it is compared, and it's normalized to unity, and it's compared to the nuclear form factor squared, which correspond to the situation when the effect of nuclear shadowing decouples from the T dependence. So we see that the correct use of this sort of the two gluon form factor, or of the gluon GPDs in the special limit x1 equals x2 is given by the difference between these two curves. And if you quantify it, you see that they differ, the shift between the minima of the two distributions leads to 5 to 11% broadening in the impact parameter space of the gluon nuclei PDF. The similar effect, the similar shift towards of the diffractive minima towards smaller x is called by another physical effect, by the effect of saturation, and that has been discussed in the literature by several authors. As again, in our approach, the shift has nothing to do with saturation. It's merely an effect of large leading twist gluon shadowing, which leads to the coupling of the T and X dependence. Another process where this effect, this shift can be seen is for instance at EIC, and the shift will lead to dramatic oscillations of beam spin nuclear DVCS asymmetries in DVCS on nuclei in the collider kinematics, that is at EIC or LHEC. Okay, so let me conclude and summarize. Small x nuclear PDFs, especially in the gluon channel, are poorly constrained at the moment by available fixed target data. However, more measurements are coming and more processes are being offered. Therefore, one really hopes that additional processes and run-to data will help to improve the situation with very large uncertainties of nuclear PDFs at small x. The process that we've been advertising over the last several years is photoproduction of JSI in lead-lead ultraperipheral collisions at the LHC, which in the approach that we used gives direct evidence to large gluon shadowing, and thus allows to constrain it quite significantly down to 10 to the minus 3. The theoretical challenge I explained you in some detail, the simple phenomenological approach that we used and the issues that people have been discussing in the literature. So to take a serious look at this process, the biggest theoretical challenge and open question is to include the data on exclusive JSI photoproduction on nuclei in global QCD fits using on the same footing as inclusive data. To do that, one has to develop a theoretical framework, NLO PQCD framework, which should be as rigorous as our usual collinear approximation for inclusive processes. And finally, obviously, heavy quarkonia photoproduction UPCs gives an access to transverse imaging of nuclear gluons at small x, but again, to make the statement more rigorous, it requires more theoretical input and more theoretical analysis to make such statements more quantitative. Okay, that's all I wanted to say today. Thank you for your attention.
Vadim, can you hear us from here?
Yeah, fine. Thank you. Yes, I can.
Thank you very much for the presentation. It was really very nice that you summarized the theoretical issues in JSI production, leading order, next to leading order. It was the perfect summary of our discussion yesterday. It was almost as if you had been there. So, any questions for Vadim?
Yeah, I just echo what both you and Vadim say. It's important to do the really good, honest next leading order calculations. But the formalism you presented involving the wave function origin. That's what traditionally used. If you go beyond leading order, if you try to calculate short distance hotpotch, you will have to deal with the normalization of that particular quantity. You can do NRQCD for the exclusive process to handle that more systematically, because you require the normalization of that wave function at the origin to cancel some of the divergence of your diagram, diagrams, especially like a Coherent singularity type diagrams.
I cannot really comment on that. When I read you know, the paper by Ivanov and et al., they start by saying that, you know, we treat the final state GHI non-relativistically. There is only this O1 matrix element which enters the question, that enters the answer, and that's it. And then we expand in alpha S the rest. So I'm an expert in it. I cannot really comment if they make an erroneous approximation there or oversimplified things. I can only repeat what was written in their paper, and you know, my interpretation is that, yeah, the starting point is, yeah, one matrix element for the GSI wave function, non-relativistic collinear charm anti-charm quarks in the final state, and then we treat the loop at next to leading order, and that's the content of their paper. It's the same matrix element for the charmonium final state at leading order, at next to leading order in their approach. There's no difference there.
I understand what you say, but if you look at the diagram, if you add the gluon between your quark momentum Q1 and the anti-quark momentum minus Q2, since both gluon parallel moving together, then that, like, not both quark are moving parallel together, then when you add that gluon between, you know, immediately have a Coherent singularity. That when that gluon momentum goes soft. Then if you right-hand side is a standard NRQCD matrix element for the color singular channel, then the renormalization, you know, in principle, that matrix element will absorb that divergence into the matrix element. If you think of the leading order and the next leading order wave function origin the same, there's no way for you to absorb that divergence. So that's a common, say I read the paper, I didn't go into the detail, but I say the idea to go to next leading order is very, very important. Only thing I say here, like we discussed yesterday, it's important to do a straightforward calculation to define everything, so we can see what now compare to that.
Okay, well, you're the expert, so yeah.
I can only say, okay, what I said yesterday. Okay, so if you this part, okay, what you are saying, okay, we discussed, okay, in our paper, and since we are using framework of conventional regularization, okay, this part, okay, also this is our step, and this is okay, so somehow okay discussed, okay, in papers of some others.
Yeah, as I said yesterday, we can discuss in detail how to handle it. I think a general idea to do a good, solid next linear correction is very, very important. Especially when you find the correction of 200%, that means we like to identify exactly how to handle that big correction and have confidence for the, say, next linear correction will not be strong.
The only, okay, I want to say that at the same time, okay, we are doing raw production, but this issue does not exist. Okay, and also for raw electron production, correct and raw corrections were. Okay. So
that's we dealing with a heavy coordinate.
No, but this is a different issue because this is an X-independent correction, right? So the problem is, of course, there's no X.
Can I ask okay, Vadim, I have on your page 5, yes? Okay, you was discussing different processes. Okay, if I am right. Yes, exactly. So tell me please. Okay, do you see some kind of in those processes KT factorization is somehow more adequate in comparison with collinear factorization?
For all of them, or for is there a particular process from the list that I mentioned that is more appropriate?
That collinear factorization, okay, does not lead to somehow
Sure.
right result, but KT.
Yeah. Well, probably the processes which have the smallest scale are, you know, more suitable to be treated within the KT factorization. That is the first two, J psi and psi prime. If you want to compare collinear approach and the KT factorization approach, for the first one, they're probably very competitive. Compared to dijets, for dijets, okay, again, it's, you know, there are two schools of thought, but for dijets, PT of jets, it's 20 GeVs. So, and we know that the collinear framework at HERA for photoproduction works very well. So there's no question that one can straightforwardly use the collinear factorization with nuclei PDFs, photon PDFs, and make predictions which will be quite reliable for, say, inclusive dijet photoproduction UPCs. So regarding upsilon, again, it's a bit hard to say to me in principle. Yeah. So what's done in the literature, it's a bit of a mixture of collinear approximation and KT factorization by the Durham group. But they have successful phenomenology if you look at the data. But at leading order, at next to leading order, they describe both J psi and upsilon production. So they, for instance, they fix gluon density using the J psi data and go ahead and make predictions for upsilon, which describe the data fairly well. And raw is, of course, it's a soft process, so don't have to think of, you know, we don't have to discuss raw in the context of GPDs or KT factorization at all. Yeah.
Vadim, in some point you have shown that you use this Shuvaev transform to generate psi dependence of the GPDs from Diglap evolution.
Yeah.
Exactly. So in this point, does it literally mean you have it's just perturbative effects which generate the skewness? I mean, we know that there is this famous Polyakov price terms which live only in the urban region, and actually they could be, this D term could be very large for nuclei, and there's no way to generate something like this perturbatively for evolution. So it's some non-perturbative, basic non-perturbative information. So did somebody try to add such D term and see how this changes the ratio? Maybe it would be some effect.
I don't think that the D term contributes at all to this amplitude, because we take the imaginary part, therefore that pushes us to the x equals psi boundary, and this is there is no D term here. We're sitting at the boundary of the Diglap region for the GPDs. We talk about high energies, imaginary part of the amplitudes. So it's all Diglap region, and in this crossover line, there is no D term there, so it's not relevant.
But but one can do also this small psi expansion. So like more or less like a Taylor expansion in psi, and then the leading term would be just PDFs with some T dependence, and the next term would be basically, I think Shuvaev and Maxime call it this B2, of X. This would be literally the determined integrals over X. So, I mean, there's like everything contributes everywhere.
Everything contributes everywhere. This, I don't know, I'm afraid to say something wrong. So my first impression was that it's not relevant. It's high energy is D-term is something which is energy independent, X independent. So it should not affect the prediction that we're going to discuss. But again, I'll have to see if what I'm saying is indeed 100% correct, that the term is completely irrelevant for the amplitude at leading order that we're discussing. Yeah. But but regarding the skewness correction, phenomenologically what we did, we just I took a look at the X dependence of nuclear gluon distribution, of the proton gluon distribution. I found this at small x. I found this parameter lambda. I saw that it's slightly different for nuclear gluons and for the gluon distributions in the proton. I used this lambda in the skewness factor and took the ratio of the two skewness factors and found the kappa, and kappa was 0.9, 0.95, so very close to unity. And I didn't run the skewed evolution because, sort of the skewness factor was applied after the evolving separately, usual gluon nuclear and usual gluon proton PDFs to the required scale, 3 GeV squared, and on top I applied the Chauvet transform. That's sort of the idea of this approach. Yeah.
I have a more, I would say, experimental question. So nuclear shadowing is an initial state modification. So what about final state effects in coherent J-psi production on the nucleus? So it's a bit tricky because you're discussing the coherent production on the nucleus, but still, since you're comparing with production on the nucleon. As a question, is it could there be say modifications to coherent production on the nucleus that result from, say, more or less incoherent production on the nucleons and some final state modifications, a rescattering of the J-psi with nucleons, and altogether ending up in a coherent nuclear final state? Corrections which are not included in the initial state modification, nuclear shadowing.
Yeah. So what you seem to be discussing is that some additional rescattering which leads to factorization breaking for this process on nuclei.
In a sense, yes. Yeah, it would be it would be factorization breaking. Yeah.
Factorization breaking. I don't know. I haven't studied it. I haven't seen anything like that for exclusive processes. Of course, for inclusive GSI photoproduction, there are
that issue very relevant.
Yeah. There it's relevant, and people discuss it because it's relevant for many other things, right? For heavy ion collisions. Here, again, as I said, it would be clearly a step in the direction beyond the whole framework that we use. That when we stay with the collinear factorization, collinear quantities, when we have universality, and this sort of in a way this is maybe the end of story. Yeah, if you want to include the effects that,
I mean, logically, your framework is certainly consistent. It's more like a practical question. Say, suppose you had a very thick nucleus, would there be some factorization breaking effects that are enhanced by the nuclear thickness, or something like violations of color transparency of the outgoing CC bar? But I think you're absolutely right. This should be discussed as violations of factorization.
Or is it higher twist? Is it power operations?
It doesn't have to be higher twist. It can be I mean, one could imagine some trajectories where the production on the individual nucleon is strictly increased, but then the coherent nuclear state emerges through some rescattering of the J psi on the nucleon. So that and I think, but Vadim is right. I mean, it's really a factorization breaking. Okay. I don't think there are any further questions for Vadim. So let's thank Vadim again. Are you going to hang out with us for some more time?